Section 6.2, we're looking at properties of power series, and one of the main things that we want to look at is how can we use these properties to combine power series in different ways to form new power series, thereby expanding the range of functions or the set of functions that we can write down a power series for. So let's look at combining power series, starting with addition. Addition and subtraction are going to work basically the same way. Here's our theorem. Suppose that I have a function written as a power series f of x and a second function written as a power series g of x. Then if I add these two together, that will converge to a power series f of x plus g of x. So you can see here I have the terms of f and the terms of g added in a single power series that will converge, and it converges to f plus g. Okay. The interval of convergences all have to overlap. The next piece says that, okay, let's focus on this function f, right? Cn x to the n. If I take any real number b, I can multiply in a constant, and I can multiply in x to any power. And that'll still converge. Now this says that the powers have to be positive because otherwise it's not a power series anymore, right? If you have dividing by x. Okay, and then this third property says, suppose I have a real number once again, and I have a positive integer, so that we're going to take x to a power. What we're doing here is composing, right? We're plugging this bx to the m in for where there used to be an x, okay? And so on my function, I've replaced the x with bx to the m. So we can do composition, and that works out just fine too. Okay, so we can add power series. We can multiply by constants, including powers of x. And property 3 is we can do composition. Okay, so let's see how we can use these properties to find a new power series. So let's look at an example. Find a power series for this function. F of x is 3x over 1 plus x squared. A good starting point for most of these is going to be using the geometric series. Okay, so a over 1 minus r is the sum from n equals 0 to infinity of x to the n. Okay. Getting a little ahead of myself. A over 1 minus r is the sum of a r to the n. Okay. So in this case, if I let my r be the opposite of x squared, set r equal to negative x squared and a equal to 3x. Okay. Let's do this problem two different ways. Okay, so the first way that I can go about finding a power series, I know from the geometric series that 1 over 1 minus x is the sum from 0 to infinity of x to the n. Okay, and then using the properties that we just talked about, if I want to have a positive x squared here instead of a minus x, I can do composition on both sides, where I replace my x with a negative x squared. So on the left, I'll have 1 over 1 minus negative x squared. And on the right, I'll have the sum negative x squared to the n. Okay, and simplifying both, on the left, that'll give me 1 over 1 plus x squared. On the right, it'll give me the sum from 0 to infinity, negative 1 to the n, x to the 2n. Okay, and now I'm going to multiply in, because we said we can multiply in both constants and powers of x. I'm going to multiply by 3x. So on the left, I'll have a 3x over 1 plus x squared. And on the right, when I multiply in a 3x, I'll have a 3. When I multiply an x times an x to the 2n, I'll have an x to the 2n plus 1. Okay, so here we explicitly used our properties in order to find a power series for this function. Okay, let's look at another way that we can go about doing this. This still uses the same properties, but they're not as explicitly stated. So I know from geometric series that a over 1 minus r is the sum of ar to the n. Right? And again, using my properties, I know that I can do things like composition and multiply and so on. So one of the things I could do is just pick an appropriate value for a and r, and it's okay if they are have variables in them, right, of x. Okay, so what I'm going to do is I'm going to let r be the opposite of x squared, and I'm going to let a equal 3x. So on the left, I'll have 3x over 1 minus a negative x squared. So that's the function I was looking for. And on the right, the a is 3x, and then the r is negative x squared, which is to the n. Okay. So I have a negative to the n, so let's say negative 1 to the n. X squared to the n is x to the 2n. And now I can combine up my x's and get a sum from 0 to infinity of 3. I have a negative 1 to the n. And now when I combine up the x's, I'll have x to the 2n plus 1. Okay, so you can see it's the same series. Just a different way of going about the same steps. All right, let's look at another example. Find a power series for this one. This one is a little bit more complicated because I don't have the same sort of setup. I can't get this through just composition of that a over 1 minus r business. So what I'm going to do is I'm going to start this off differently. I'm going to rewrite my original function using partial fractions. Okay, so let's start off that way. Let me solve this partial fractions. So multiplying through by the denominator, I would get 1 equals a times x minus 3 plus b times x minus 1. And I'm going to use strategic substitution. When x is equal to 1, on the left I have 1, on the right I have 1 minus 3, and over here by the b I'll have a 0. So 1 is negative 2a, so a is negative 1/2. When x is equal to 3, I'll have 1 equals a times 0 plus b times 3 minus 1. So 1 equals 2b, so b is a positive 1/2. Okay, so I can see now that this is equal to a negative 1/2 over x minus 1 plus a positive 1/2 over x minus 3. Okay, now what I want to do is for each one of these individually, I want to find a power series, and then we'll add them together. And we're going to do something similar to what we did up here. Okay? I know from geometric series this 1 over 1 minus x is the sum of x to the n. And I say, all right, can I get this thing? Now, this isn't 1 minus x, this is x minus 1, okay? But that's just off by a negative. Okay. So write this as positive half over 1 minus x, and then plus negative half over 3 minus x. Okay, now in the formula that we had, 1 over 1 minus x, or even if I use a over 1 minus r, either way, this 1 is stuck as a 1. And for the first one, that's not a problem. I have a 1 here. But this 3 is going to be a problem. So what I can do is I can take this second fraction, and you could think of factoring out a third or multiplying numerator and denominator by 1/3. So I have a half over 1 minus x plus a negative 1/6 over 1 minus x over 3. Okay. And now we're in business. Okay. So for this one on the left, if I do the a over 1 minus r, it's the sum 0 to infinity of a r to the n. I'm going to pick a to be 1/2 and pick r to be x. So 1/2 over 1 minus x is going to be the sum of 1/2 times x to the n. Okay, so that part looks good. For this one, if I pick the a to be negative 1/6 and I pick the r to be x over 3, okay, I'll have a negative 1/6 over 1 minus x over 3 equals the sum from 0 to infinity, negative 1/6 times x over 3 to the n. Okay, now this 1/6, I don't have to do it this way, but I can write it as a half times a third. So I have a negative 1 over 2 times 3. And the reason I'm going to do that is because over here I can write this as a 3 to the n in the denominator and an x to the n in the numerator. And I can combine up these 3's. So I have a negative x to the n over 6 times, I'm sorry, just split those up. A 2 times 3 to the n plus 1. Okay. So now getting back to my original function. So 1 over x minus 1 times x minus 3, I know is a half over 1 minus x plus a negative 1/6 over 1 minus x over 3. So I can write this as two different series, sum from 0 to infinity 1/2 x to the n plus the sum 0 to infinity negative 1 x to the n 2 times 3 to the n plus 1. So now we're going to add the series together. The way to add series together is to match up the powers of x. Okay, and in here, I think that's easy to do because I have a sum from 0, right? So it's starting at the same spot, and they're both x to the n's. Okay, if it gets more complicated, you might have to write out a few terms just to see how it starts. Okay, but now I can write this as like one big thing, right? Add these two together. Okay, and then it just depends on how fancy you want to get with this. So the easiest step to do is just to factor out the x to the n. So I have 1/2 plus negative 1 over 2 times 3 to the n plus 1, x to the n. Okay, and I think in many cases this will probably be sufficient. Okay, but if you wanted to maybe clean this up a little bit, then just on the left, what we're going to do is get a common denominator. So I'm going to multiply by 3 to the n plus 1 on top and bottom here. So I'm going to have 3 to the n plus 1 minus 1 over 2 times 3 to the n plus 1 times x to the n. Okay, so that's a series for our function. Okay, let's look at another one where we're adding, in this case, subtracting series. And in this one, I think that things are going to not line, or it can get complicated in a way that's hard to see at the beginning. So find a power series for f of x minus g of x over 2. Okay. I think what gets weird with this one is that when I subtract, some of the terms are going to cancel out, but not all of them. So let me just write out the first few terms of f of x, right? So when n is 0, I'm going to have 2 over 3, and then x to the 0, right? So that's it. And then when n is 1, I'll have 3 over 4, x to the 1. And when n is 2, 2 plus 2 is 4, right? Over 5, x squared, plus 5 over 6x cubed, and goes on from there. Okay. When I write out the g of x, I've got a negative in here, right? So when n is 0, negative to 0 goes away, right? So I'm just going to have a positive 2/3. But when n is 1, I'll have a negative. Okay, but otherwise I have the exact same terms. So it's the same series, but this one alternates. Okay, so now when I take f of x minus g of x, and we'll deal with the half later, if I write out what does negative g of x look like, maybe it's easier to add. I'll have a negative 2/3, a positive 3/4 x, and negative 4/5 x squared, positive 5/6 x cubed, right? Minus, and so on. So when I add these together, the 2/3 cancel, and then the 3/4 double up, and then the 4/5 cancel, and then the 5/6 x to the cube, that the cube term doubles up, right? And then cancel, and then double up, and so on. So if I take half of this, then that just cancels out all the doubling up. Okay, so what makes this one complicated is that if I want to go to write a series now, every other term is 0, but I don't write series that way. I don't have a mechanism to say, okay, my series are going to be these terms, except every other one just magically becomes a 0. We don't really have that in our notation. So what I want to do is I want to sort of look at what I have and start fresh and say, how do I write this as a series? Okay, so might be helpful if I had another couple terms in here. Okay, so the next term, right, would have been 6/7 x to the 4th, and then a 7/8 x to the 5th, right, and so on from there. So the next one that doubles up, right, the 6th, 7th one would have canceled, right, but the 7/8 one would have doubled up, 7/8 x to the 5th. So when I multiply that in by half, the doubling up cancels. We have that 7/8 x to the 5th. Okay, and I think this is enough to see a pattern off of, right? Okay. So I want to write a power series now, starting with n equals 0. And my, let's first get the constants, right? So if n is 0, this numerator is 3 bigger. But my numerators are going up by 2's, so I want a 2n in here. Okay, and then if I want to start at 3, I have to have a plus 3. My denominators are also counting by 2's, so 2n. I start at 4. Okay, so now when n is 0, I'll have 3/4. When n is 1, I'll have 5. And down here, 6. Good. When n is 2, I'll have 4 plus 3 is 7. Good. 4 plus 4 is 8. Good. Okay, so I've got my constants lined up. Now for the powers, again, the powers are counting by 2, so I need a 2n. And when n is 0, I want to have a power of 1, so I add 1. Okay. So here, rather than leave them as generic terms when I add them together, because of the canceling, it might be easier to have written out a few terms, identify the pattern, right, and then sort of recreate your series from scratch. Okay. So let's look at another example. Once again, I can see that I have these multiply denominators, so I'm going to start by using partial fractions. I'm going to go ahead and factor that x squared minus 1 into x plus 1 times x minus 1. The x squared plus 4 is a fully factored, it's an irreducible quadratic. So when I go to write this out, I have a irreducible quadratic, so like an ax plus b over x squared plus 4, and then c over x plus 1, and then d over x minus 1. Okay. If I multiply through by the denominator, on the left I'm going to have 5. On the right I have ax plus b times x plus 1 times x minus 1. And then c times ax, not ax plus b. C times x squared plus 4 times x minus 1. The x plus 1's cancel. And then the d term, the x minus 1's cancel, so I'll have d times x squared plus 4, x plus 1. Okay, again, I want to try strategic substitution. When x is equal to 1, on the left I have 5, on the right I have a 0, I have a 0, and then here I have d times 1 squared plus 4 times 1 plus 1. Okay, so 5 equals d times 5 times 2. So 1/2 equals d. Okay. When x is negative 1, on the left I'll have a 5. On the right I have a 0. Here, when x is negative 1, I'll have c negative 1 squared plus 4, negative 1 minus 1. And here, when I put in negative 1, I'll get a 0. So 5 equals c times negative 1 squared is 1, plus 4 is 5. Negative 1 minus 1 is a negative 2. Cancel the 5's, so negative 1/2 equals c. Okay, I won't be able to get the a and the b with strategic substitution. So now what I think I'll do is maybe multiply this out and equate coefficients. So foiling out this first one, I'll have ax plus b times, if I write this as x squared minus 1, right? I'll do it in 2 steps. For the c term, I think I can just start foiling it out, right? So x squared times x is x cubed. minus x squared plus 4x minus 4. And here, I'll have x cubed plus x squared plus 4x plus 4. Okay, multiplying the ax, so I have ax cubed minus ax plus bx squared minus b, and then distribute the c, and then distribute the d, okay. But I can plug in d is a half and c is a negative half. So here I'm going to have a negative half x cubed minus a negative half x squared. Negative half times 4 is minus 2. And then a negative half times a negative 4 is a positive 2. D is a positive half, so I have a half x cubed plus a half x squared plus 2x plus 2. Okay, so let's equate coefficients. Let's start with the x cubes. On the left, I have 0 of them. On the right, I have a minus 1/2 plus 1/2. Okay, so 0 equals a. And now let's look at the x squareds. On the left, I have 0 of them. On the right, I have bx squared plus a half x squared plus a half x squared. So 0 equals b plus 1, so b is negative 1. Okay. So now I have my partial fraction decomposition, right? b is negative 1, a is 0, so we have negative 1 over x squared plus 4 plus a negative half over x plus 1 plus a positive half over x minus 1. Okay. All right, good. Now, for setting these up for series, instead of starting with the x's, I want to start with the constants. Okay. So let's do these one at a time. We'll start with the negative 1 over x squared plus 4. I'm going to rewrite this as negative 1 over 4 plus x squared, and then multiply the top and bottom by 1/4. Just like we did before, because I like to have a 1 in this first spot. So I have a negative 1/4 over 1 plus x squared over 4. Okay. And I know a over 1 minus r is the sum of ar to the n. So I'm going to pick a to be a negative 4th, and I'm going to pick my r, because I want a minus, right? I'm going to pick this to be a negative x squared over 4. Okay. So this is going to be the sum from 0 to infinity of negative 1/4 times negative x squared over 4 to the n. So I have a negative 1/4 times a negative 1 to the n, x to the 2n over 4 to the n. And now let's combine up our factors, a negative and another negative, right? Add the powers, so I have n plus 1. The x is just hanging out. And 4 times 4 to the n is 4 to the n plus 1. Okay, so I have a power series for this first piece. Okay, now let's look at the second piece. Negative half over x plus 1. Okay, so once again, let me write this as a 1 plus x I want my a to be a negative half, and my r to be the opposite of x. So then this is going to become the sum of negative 1/2 times opposite of x to the n. So I have a negative to the n and another negative, so a negative to the n plus 1, x to the n, and 2 doesn't have an n power on it, it's just the 2. Okay. Finally, I have a positive half over x minus 1. Okay. So if I multiply top and bottom by a negative, I'll have a negative half over 1 minus x. So I want my a to be a negative half and my r to just be x. So this is going to be the sum of negative 1/2 x to the n. Okay. So now if I take my original function, it's these three series added together. So my function was 5 over x squared plus 4, x squared minus 1. So what I'm going to do is I'm going to add these three series. Okay. Now adding these first two, I think, is going to be a little bit more straightforward, like the one that we did before, because the powers of x line up. But here, I only have every other power. I only have the even powers of x. Okay, so it's going to look a little bit more complicated. If I write out what the terms would look like, for this first one, when n is 0, right, I get my constant, right, so a negative over 4, right, and x to the 0, okay? And then for my next power, when n is 1, I'll have a positive 1 over 4 squared, x squared, right? And then a negative over 4 to the third, x to the fourth, right? And so on. Okay. These other ones have every single power of x. And so just like before we had that issue where I couldn't write a series where every other term was 0, I'm not going to be able to write a series where all of the even terms have a different thing added than the odd ones. Okay. So combining these together isn't going to go very well, I guess is the point. So I say, shoot, is there a way we could have redone this, right? Well, back at the beginning, I said we could factor this, right, all the way. And that's how we do partial fractions. But maybe instead of finding a separate power series for c over x plus 1 and d over x minus 1, if I had combined them together and had an x squared minus 1, then I'd have an x squared in my fraction. And so in my power series, maybe I'll have an x to the 2n, and things will line up nicely. So let me back it up a little bit and say, okay, what if I combine these two? Okay. So what if I take a negative half over x plus 1 and then a positive half over x minus 1, and I get common denominators and combine them. Okay. So then I have negative half x plus a half, and then a half x plus a half over x squared minus 1. The x's cancel, the halves add up, so I get 1 over x squared minus 1. Okay, and I convert this one to a power series. Okay, so I'm going to write this as 1 over 1 minus, negative 1 over 1 minus x squared. Okay, so let's let the a equal negative 1 and the r equal x squared. So I get that this thing is the sum from 0 to infinity of negative 1 times x squared to the n, or negative 1 x to the 2n. Okay, now I can combine this one and this one without too much trouble. Okay, so let's try that. So I have 5 over x squared plus 4 times x squared minus 1 equals my green series here, 0 to infinity, negative 1 to the n plus 1 over 4 to the n plus 1 x to the 2n. Okay, and now my new series here, sum 0 to infinity, negative 1 x to the 2n. So now when I add these together, when I have the common x terms, I can just add the fractions. So I have a negative 1 to the n plus 1, 4 to the n plus 1, minus 1. Okay. And if you want to get common denominators or something like that, mess with that and combine it, you can. But at this point, we have a legitimate power series for our function. So I think we're going to call it a day on that one. Okay. Next up, this one is a little bit tricky. Express the sum express this sum, right, as a geometric series and then turn it into a rational function. If I look at this, the first thing to do is identify the pattern, right? So I have increasing powers of x, good, increasing powers of 2, good. Right, so I can think of this as like x over 2, x squared over 2 squared, x cubed over 2 cubed, x to the 4th over 2 to the 4th, x to the 5th over 2 to the 5th, x to the 6th over 2 to the 6th, right, and so on. Except that one is negative, and well, this one is negative. But it's not every other term. It's every third term. So when I look for a repeating pattern, I have a block of 3 where the pattern repeats. Okay, so when I go to write this thing as a geometric series, it's not as simple as just saying, okay, you know, I've got this half power, right? So maybe I have like an x over 2 to the n or something like that, because I have a negative but only every third term. So I'm going to take these blocks of 3. So what I'm going to do is I can say, well, within the block of 3, now I have a repeating pattern. So if I look at the first piece of every block of 3 that I would get, the first piece is going to look like an x over 2, an x to the 4th over 2 to the 4th, right? What would be the next one, right? It would be a power of 7, x to the 7th over 2 to the 7th. Okay, now I look at the second one in every block of 3. So I have an x squared over 2 squared, an x to the 5th over 2 to the 5th, what would be the next one, right? After 7, I'll have an 8. X to the 8th over 2 to the 8th. Okay. And then finally, let's look at the third terms. The third terms are all negative, so I'll just write minus and then just write them as positives. So I have an x cubed over 2 to the third, and x to the 6th over 2 to the 6th. The next one here, after 7, 8, would be an x to the 9th over 2 to the 9th. Okay. And so what I'm going to do is I'm going to write each one of these as its own separate geometric series. Okay. So I have to identify the pattern, right? So my x's are going up as powers of 3. So I want an x to the 3n. But when n is 0, I want to have a power of 1, so add 1 on there. Okay. The powers of 2 match the powers on x. Okay. Let's do the same thing for the second piece. So here, again, I'm going up by 3's. So I want 3n. And when n is 0, I want to have a power of 2, so we'll add 2. And the powers of 2 match the powers on x. So I have 2 to the 3n plus 2. Okay. Here again, I'm going up by powers of 3. Just do like a plus 3 here. No need to get fancy and have n start at 1 or something silly like that, because we want to combine these together. Okay, so I've now expressed this as series. In order to make this look like a geometric series, I want to make it look like a r to the n for each one. So for the blue one here, let's break off these plus 1's because they don't have an n in them. So I'll have an x over 2 times x to the 3n over 2 to the 3n. And now I can break this off as an x cubed over 8 all to the power of n. Okay. So this is my a and my r. So this is going to be x over 2 divided by 1 minus x cubed over 8. I say, all right, fantastic. Let's move on to the next one. Basically the same idea, right? You can just repeat this. So it's really messy looking sum. Let's fix that. Okay, so I'll have an x squared over 2 squared times x to the 3n over 2 to the 3n. Okay, so we have x squared over 4. And here I have an x cubed over 8 all to the n. So again, I have my a and my r. So I'm going to have an x squared over 4 all over 1 minus x cubed over 8. Okay, and then the last one. Here we have an x cubed over 2 cubed, x to the 3n over 2 to the 3n. Do the same thing. This as x cubed over 2 cubed to the n. So I have x cubed over 2 cubed divided by 1 minus x cubed over 8. And this is nice, they all have the exact same denominator, so I can combine them all together into one fraction. Okay, so I have an x over 2, x squared over 4, and minus x cubed over 8. And then I'm just going to multiply numerator and denominator by 8. So 8 over 2 is, well, yeah, 8 over 2 is 4. 8 over 4 is 2. Okay, 8's cancel, and in the denominator I'll have an 8 minus x cubed. So there's my rational function.